Hello, everyone, and welcome to the latest edition of Axelar Learn. I'm here with Axelar co-founder Sergey Gorbunov. Hi, Sergey.
Hey, everyone. How are you doing?
We're going to talk about quadratic voting today. It's a super timely topic. Why? Because the Ethereum merge has just been completed. Ethereum ticking away block by block. Glad to see it. And, what does quadratic voting have to do with the Ethereum merge? As everyone knows, the merge is Ethereum's move from proof of work to proof of stake. And quadratic voting is a important but somewhat sadly neglected concept in proof of stake governance. So we're going to get into what it is today. We're going to talk a little bit about it. As many of you may know, Axelar implemented quadratic voting as part of its cross-chain security model in its last upgrade, codenamed MAVE. And we're going to talk a little bit about Axelar's network, Axelar system structure, and get into some of the kind of nitty gritty of quadratic voting as well. So without further ado, Sergey, why don't we start off just kind of giving listeners, viewers here a sense of how does Axelar work? What is the the setup of the network? And if I can get my screen share here, I will start by sharing a view of the tech stack diagram. So go ahead and kind of start to explain it, and I'll see if I can get that rolling.
Yeah, sounds good. I mean, in a high level, Axelar network is a permissionless proof of stake network that routes messages across different blockchains, right? So the setup is that you have a notion of a gateway or a router that kind of sits on every chain, which is a smart contract. Any application or the user can write a message to this gateway. And then from there, the Axelar validators are collectively monitoring these gateways and deciding what needs to happen to those messages, right? So they're running a consensus protocol to finalize decisions on those messages, where they need to be routed, where they need to go, and subsequently from there, the messages are getting routed and delivered, right? So the network itself does all the heavy lifting when it comes to message processing, but for the applications and users, it's then a very simple integration point where they can access this functionality from a simple API call from any chain that they reside on, right? So if you have your application on Ethereum, then Ethereum application can call this gateway and a router, and that's it. You don't have to think about all the other complexity. So everything is sort of abstracted away behind the scenes, and then the network itself does all the kind of security validation process and routing, translation, and kind of everything else, right?
And we should talk about that a little bit, because the network itself is actually a blockchain, right? It's a blockchain connecting blockchains. And so what are the implications of having a proof of stake blockchain in the middle, both in terms of security and functionality?
Yeah. I mean, in terms of security, right, it gives you the most robust way to deliver messages across blockchains that cannot talk to one another directly, right? What that means is that the proof of stake model of the Axelar chain is analogous to many of the proof of stake models that the chains that we connect, actually, right? So that's one point to make, and that comes with very strong kind of security and robustness and liveness properties, behind the scenes corresponding to it. So that's on the security side, and then on the functionality side, having a blockchain really allows it to program it to deliver superior features at a cost-effective and efficient way, right? So as an example, whenever you are sending messages from blockchain, let's say that speaks Solidity, right, to a blockchain that speaks like Cosmos IBC, right, it's a very different message format and it's a very different transaction format. So somebody needs to translate those messages from one format to another, right? So where do you do this in an accountable and verifiable and secure way? You can put it sort of at the application edges and then have to pay gas all the time for those things. That would be very costly, right? Or you can do it at the network layer. And so Axel does it sort of at the network layer and allows you to do it very, very efficiently. So that's one thing. And second, we can have various functionalities that make the user experience even more superior baked in at the network layer. So one example is actually this feature that we call as a deposit address on Axelar, right? So for those of you that haven't seen, I actually encourage you to kind of go to Osmosis Dex and kind of check it out. They rolled it out actually yesterday, where you can go to Osmosis, you can generate the deposit address for assets from Ethereum, let's say USDC, and then send your asset directly from like a centralized exchange, right, or any wallet that you have, and that asset will automatically arrive in your Osmosis app and display in your wallet, and that's it, right? Like you don't have to even touch Ethereum in that model, right? You don't ever have to have a gas on Ethereum in that model. You don't ever have to touch Axelar, right, or any of the relay in the middle. So it's actually like a multi-hop process with multiple layers of routing behind the scenes. But for you, you can go from Coinbase and just directly deposit like USDC in Osmosis with one click. And how is it possible is because on Axelar network being a blockchain, we kind of program the functionality to say USDC, when it comes to this deposit address, needs to be routed to Osmosis. Okay, so that's functionality that Axelar network is aware of, and so as soon as the funds arrive, then the rest of the transaction flow, happens, and the assets arrive at the destination. So it's a kind of an example of a programmability that you can do then at the network layer to deliver this type of UX that would not be possible otherwise, and users would have to like interact with MetaMask and pay Ether gas and so on and so forth.
Yeah, no, that's cool. We talk a lot about Osmosis, but they really, I think, are the first or one of the very earlier projects to see this this vision. Osmosis is, I think, the largest DEX on Cosmos, and I think we're fortunate to now be working with some of the largest DEXs on multiple networks, Avalanche, Near Protocol recently. But I think, Osmosis, like from very early days, saw this vision of an on-ramp for DeFi and for decentralized applications that is similar to, as easy as what users experience in a centralized exchange. And I think we have a lot of partners now who are excited about this, kind of looking ahead to the next wave, right? Like what in the last wave of crypto, DeFi certainly drove what was going on. Decentralized applications drove a lot of the enthusiasm, but a lot of the flow of users went in via centralized on-ramps. Could it be possible that in the next wave we see that that volume of flow of users, of millions of users coming in straight via decentralized applications? So you mentioned the kind of the security at the center, and maybe we should talk a little bit about kind of what that looks like in terms of validator activity and voting, the AXL token, which powers this activity, and the security model is scheduled for release in T-minus 11 days on September 27, and we're excited about this milestone and kind of the security approach that Axelar is pioneering here. So, Sergey, if you could kind of walk us through, this is a fairly new diagram that we've just created, and kind of what goes through all the steps that a user request takes on its way through the Axelar network. So, what are we looking at here, Sergey?
Yeah, I mean, we're looking at a lot of boxes and a lot of steps. So let me.
It's a twister board, actually. I think I feel like it's a board game that I'm interested in maybe playing someday.
Yeah, no, I mean, like if somebody can tokenize this, right? I think but let me try to go, from right, kind of in a clockwise direction, right? So kind of trace through some of the steps. So this is kind of a journey that a user request takes. So first of all, I guess I want to say by saying that the user does only one click, which is step one, and then the rest of the flow they don't need to worry about, right? So the rest of the flow here, all the steps, 2, 3, 4, up to 7, is everything that's done automatically by the infrastructure and the network behind the scenes, right? So don't get confused that this is not what you have to interact with. And I think we should make that clear on the diagram.
We call it the 39 steps, right? Like the Alfred Hitchcock movie.
Yeah.
Anyway,
I only count to 10.
No, it's only one step.
And I do mod 10. But anyway, so the user, right? Suppose you want to let's do an example, right? You want to take a loan of an asset, a cross-chain loan, right? So you have like an asset on a single chain, let's say on Ethereum. You want to take a loan against this asset on a different chain, let's say Avalanche, right? So as an example, so you can have an application that does this, where the asset may or may not even need to be routed across chains or bridged. It kind of depends on the application instantiation. But from a user experience, then what happens is they perform one transaction on their front end, right? So the transaction says, give me this, execute this cross-chain loan. And they pay gas at the same time on the source chain, right? So that's what you see in the step one, where the user's request goes to the application that they want to interact with, and then they pay gas to a special contract on chain, which we call a gas receiver contract. Okay. So from there, two types of things happen. First, there is a set of relayers that take the message from the application, and then they relay it to the Axelar network. Okay, so that's what you see as like step two. And then Axelar network automatically activates to validate those requests, right? So that's what you see in step three. By validation here, what we mean is that Axelar validators, as we mentioned, monitor different gateways or those routers, right? This is where the messages kind of come and go. And then they run a consensus mechanism to agree on the state of those messages and decide what needs to be done with them. And so that's one thing. But how does all that gets covered in terms of gas costs? It actually gets covered behind the scenes by the set of services and relayers as well. So when the user initiated the transaction, they paid some gas to the gas receiver, right? And they could have paid in the native currency of the chain that they transacted with. So let's say Ether, for simplicity. So then that Ether will automatically get converted into two other tokens. One is the Axelar token, and one is a token that needs to be used to pay gas on the destination chain. So when step two is then executed by the relayers, that step is also, comes with its own Axelar token that gets paid to the validators and the network to process that message on the network layer, right? And then subsequently, when the network validates it and the validators kind of co-sign it, anybody can take the message from Axelar network and relay to the destination chain to be executed, right? And so if you kind of go through some of the infrastructure and relayers that exist out there, then those relayers will also take the token for the destination chain all the way from the original transaction that the user paid and use it to pay gas and the destination chain, right? And actually execute the user request, and then the result of that, let's say cross-chain loan, is delivered back to the user's wallet, right? So then all the steps are taken care of. User doesn't have to think about it. Gas gets paid on multiple networks, so on the source chain, on the Axelar, on the destination chain, but the user never has to think about those steps, and kind of they're taken care of behind the scenes.
Awesome. Yeah, I think this is just a hugely important piece where you think about the cross-chain flow today. Acquire destination chain token, find bridge. We were joking about all the steps in this diagram, but it is truly one of the powerful features of Axelar, that this kind of transaction can happen under the hood, as it were. The user doesn't even necessarily need to be aware of chain B, like the destination chain. They may be interacting with an application. They're aware of what application they're interacting with, but what chain it's on is not something they really have to think about in this model. They only really have to think about, okay, I'm on chain A. I hold chain A token. I want to do XYZ with it. All of that logic of doing that happens kind of within a chain agnostic type of way for the end user. And of course, for the developer, there's any number of controls about how that works. But for the user, it's just a very kind of easy experience.
Yep.
So, all right, well, let's get into kind of some of the security model here. Now we're talking about quadratic voting and what that matters, what that means in a proof of stake model like this. And I think one of the issues that comes up is this question of node diversity. and really, making sure that, proof of stake is everybody, I think, has gotten on board with the idea that this is, the best way to coordinate Byzantine systems. You see all of the most powerful L1s today in Web3, they are on proof of stake. I think we still have some work to do on scalability and proving it out at larger and larger scale. But this is kind of where the exciting development in the space is happening. But let's get into some of the questions here about like what makes a proof of stake system secure, and why is why is that important? And I think that'll take us into the question of quadratic voting and how that can help improve the security of proof of stake systems.
Yeah, for sure. I mean, on the high level, look, like the more decentralization you can add to the network, right? I think the better it is, and I think it's not even for any philosophical argument. I think there's a practical security that comes with it, right? The more
let's talk about that. Like, why is decentralized more secure than centralized?
Yeah, bottom line, it increases the cost of attack, right? So in a centralized system, you have an owner, you have an operator, and anybody that needs to compromise it needs to go after that owner operator, right? There is a kind of a fixed cost associated with it, you can try exploring it with diverse decentralized systems. When they're permissionless, you allow anybody to join and be a validator, and you allow anybody to participate in the security and help operate and secure the network. And the better they do, the more usually delegations those validators have, the more resistance they show to the network, the more acceptance in the community they have, so they get more naturally more stake in the system, and they have more voting power as a result. But having a permissionless way for the validators to join and participate then means that they can choose their own setups, right? They can deploy it in their own environments with their own firewalls and networking tools and configurations, and isolate keys and isolate nodes and how they deploy it. And kind of the more diversification you have, the harder it becomes to kind of compromise such a system, right? Because you're gonna have to compromise many validators with very different software stacks, and it keeps on increasing the cost, and at some point it becomes economical and not practicable to attack all the validators, right? And it would just spend more time on it than the results of it. So that's the bottom line, right? And I think we've seen it over and over, that systems that are decentralized have very diverse validator sets coming from all over the world, right? That people contribute with it, and that leads to high safety and high liveness properties, right? Where if one data center goes down, assuming you still have majority of validators, in other data centers running or in their on-premise environments with their service providers, then the network continues running, right? And that's what we're after.
Yeah. I think it's actually a really simple analogy that you just put. Like, and actually, I think we have this in a recent blog post on the Axelar security model. You can find it at axelar.network/blog. And really, the analogy here comes down to a question of kind of diversity of nodes, and you can take it right back to any distributed system. If every node on the network is running the same operating system, and that operating system has a vulnerability, poof, right? But if you have nodes that are running diverse software, then you have a situation where, like in the kind of middle diagram here, a situation where perhaps one of those gets compromised. Look, in this diagram here, most of the network is running the same, is kind of similar, right? If that kind of node gets compromised, you have the network compromised. In a diverse network, you can see on the right in the diagram, this is the thing that proof of stake systems strive for, right? This is the goal that we need to achieve. The perhaps one kind of node is compromised, but there are many other kinds of nodes which remain robust against whatever the vulnerability is. So let's get into quadratic voting. High level, what is it? How does it make networks look more like this diagram on the right here than these two diagrams on the left?
Yeah. So on a high level, one of the problems with some of the proof of stake network becomes stake concentration, right? So what that means is that validators that do better or have more delegations to them lead to have more voting power on the network naturally, right? And so if you look at a lot of networks, you have things like Nakamoto coefficient, right, that everybody talks about, which is like the number of nodes that needs to be taken down to to affect liveness or safety of a network. And this state concentration and the result of a lot of voting power concentrated on fewer nodes leads to lower practical numbers, right, and lower security. And while it may be acceptable for base layers itself, I think when it comes to cross-chain security, the bar has to be even higher than that, right? And so then how do you deal with that, right? How do you continue increasing the validator set? How do you continue expanding it and have practical consequences on the security of it, right? Because if most of the stake is still concentrated, like in the top, 20, 30 validators, expanding the validator set doesn't actually buy you much, right? Like you have more nodes, but they have no voting power, right? Like, so you still end up practically with the same security. And so this is where
oligopoly or something. Yeah.
Yeah. So this is where the notion of quadratic voting comes in. It's not a new concept in blockchains. It's been talked about, in various settings, and it's not an easy thing to deploy. It's not an easy thing to experiment with, but I think it's actually very, very needed for the cross-chain security. So the basic idea is that if you have some stake on the network, then the votes for validating cross-chain messages are counted as a square root of that stake, right? So an example, you have 9% of the stake, you take a square root of that, you're going to get 3 votes, right? If you have 4% of the stake, then you take a kind of square root of that, right? And so you end up with 2. So and yeah, is this diagram correct now that I'm looking at it?
Well, this chart kind of looks at it like from the other direction. Like if you have 1 unit of stake, you'll have 1 vote. But if you want to get 2 votes, you'll have to accumulate 4 units of stake. And if you want 3 votes, you'll have to accumulate 9 units of stake. So what the line shows, is how it becomes more difficult as you accumulate voting power to add more voting power. The more voting power you have, the harder it is to add another incremental unit of voting power.
Yeah, exactly, right. And kind of practically what that means is that the validators that have more get less votes, but also the validators that have less voting power, let's say less than 1, they actually get a little bit more votes in the network, right? So it kind of normalizes things a little bit more, and means that then you have to take, let's say, a majority of those votes and kind of compromise the network. And practically, if you look at most stake distributions and results, that means you're going to have to compromise a lot more nodes, right, and a lot more validators, and you can continue adding more nodes on the network and validators, and kind of improve its practical security. So
I'm sorry, I'm laughing over here because I just realized there is a problem with this chart. The y-axis goes from 8,000 to 1,000. It should go from 8,000 to 10,000 and then 12,000, obviously. But sorry to interrupt.
Pretty weird looking scale.
Otherwise, the chart is good.
Yeah. I meant the typo.
This was a fat finger error that cost nobody any money.
Right. Nice. But yeah, I mean, I guess like a couple of things to note, right? There is a sort of a caveat, which I think, why I think quadratic voting is maybe it's not applicable for all settings, is that, it is possible for an attacker or an adversary to start potentially like cloning themselves, right? And trying to get more voting power than if they were just taking, running 1 node and kind of getting square root of that, which is kind of
known as a sybil attack, right?
Sybil attack, yeah. It's a valid concern. I don't think that concern is too applicable for kind of delegated proof of stake networks, right? Where, the number of validators is kind of a smaller. They're mostly, well identified people that like are fighting for more delegations from the users, right?
Right.
And any of those scenarios where the validator starts cloning usually is sort of an identifiable behavior, and there are ways to mitigate with that. So, for instance, you can actually stop things like key rotation at the Axelar network, right? If there's a behavior that validators start cloning themselves, and the key rotation will actually be sort of stopped, right? And then kind of the stake will be frozen until those situations are dealt with. So yeah, potentially like a practical concern, but I think for proof of stake networks that deal with cross-chain messages that are based on this delegated proof of stake model, I think those attacks are pretty theoretical.
So key rotation is required on the Axelar network, and what that means is that a validator must rotate their keys. That each validator has a key share which they use to sign transactions. And as we saw in the diagram earlier, there are 2 points at which validators sign transactions: one, to verify that an event has happened on a source chain, and then 2, to authorize an action on a destination chain. And for each of those, the validators have key shares and a gateway on the source and destination chain. Those key shares have to be rotated. It's a security measure to make sure that to guard against a persistent attacker who might try to compromise one validator after another. You can stop that process, and then you kind of chill out that validator who's having malicious behavior. And as you point out, there's a reputational risk to a validator. And I think that actually that reputational risk is stronger in a cross-chain network, because as we've seen with Axelar and the way we're set up, our validators operate nodes on connected chains. So for the most part, we have validators who are already running nodes on Ethereum. They're already running nodes on Avalanche. They're already running nodes on Polygon, and fill in the blank, right? They're running nodes in Cosmos, Polkadot. They have entire businesses built on validating and attracting stake in those ecosystems, and an attack like that would carry significant reputational risk.
Yeah, for sure. I think on that note, right, I think like validators are kind of some of the best, validators that have been running nodes kind of for a while, I think in some of the best positions to, operate these cross-chain networks securely, right? Because like you said, they're ready running nodes even for Axelar, right? Kind of a one way we like to refer to as sort of an overlay network, right? That monitors other chains and kind of routes messages across them. And because validators already run nodes for all those chains, then they only need to set up like an extra one node that can automatically starts monitoring and routes messages, across those environments. And, they don't have to, their cost to onboard themselves to this environment is a lot lower than for somebody that starts from scratch and then has to, spin up 7 or 8 other nodes to validate across them.
Hence the need for quadratic voting, right? You have this kind of natural kind of incumbency advantage where, people can kind of accumulate and build on, invest their edge, basically reinvest their edge. I think actually it's a broad risk across proof of stake. And I'm really interested in kind of seeing if other systems will adopt quadratic voting as Axelar has, and kind of, look for ways to kind of improve the security as we really, with Ethereum on proof of stake, move into a new era, right? With proof of stake, this is a scale at which it has not been done before. And so I think, approaches like this are going to become all the much more important.
Wasn't there some type of government or something that adopted quadratic voting like a day after we rolled it out?
Yes. The towns or cities of Jersey City in New Jersey and Nashville, Tennessee, both U.S. mid-sized cities, and
what does it mean for them?
I'm actually I need to read the article. I just read the headline and I was like, that's hilarious. I think they were actually ahead of us by a few days. So someday when everybody is running quadratic voting and governments are using these systems and to determine the good, the Jersey City and Nashville will get the first seat at the table before Axelar.
But look, like, right, like if you were to build any type of, voting system or anything like that, where you want to introduce this quadratic voting, like building that around blockchain identities would be easier than ever, right? Because, people can come with balances. You can, like, take functions of those balances, whether or not it's quadratic, like you can experiment and you can change that function to be other functions that make sense for your need or use case. But kind of having a system that everybody can refer to, right, and say, we actually understand what the actual power is and how many votes every staker will get, and then we apply our function to it, could actually lead to a better outcome. I mean, in practice, if you were to implement these things today, then there is no place you can refer to. There's no place that everybody can agree on. I think that's a bit challenging.
I think these kind of concentration of power issues are endemic all over the place, from politics to corporate governance. And I think, the most exciting thing we can be doing is kind of pioneering new modes of governance and coordination. And if you look at what people are doing, experimenting with DAOs, I mean, we talk a lot about securing, money, basically, DeFi context type of conversation, and ownership, NFTs. But honestly, like, some of the most exciting things that are happening in blockchain today are happening at, at the DAO level, and people kind of just trying out, new ways of coordinating across diverse populations. It's really exciting.
Yeah.
Cool. Well, I think we're a little bit over time. So I want to say thanks to everybody who joined, and we had a couple great questions in the chat here. If you missed the video and want to go back and look at it, you can find it on our YouTube channel. That's youtube.com/c/Axelar core. And thanks, Sergey, for running it down, and it's been a pleasure.
Awesome. Thanks everyone for joining.
See you guys.
See you. Bye.